Right, good evening, ladies and gentlemen. Lovely evening in London tonight. It's not raining. Yay! Welcome to the Royal Society. If you don't know who I am, I'm Professor Wendy Hall from the University of Southampton, a fellow of this august institute, and also privileged, I think that's the word, to be the chair of the Milner Award committee. So it's my honour to do the introductions tonight. Before that, I have just a few housekeeping housekeeping things to do. Mobile phones off, please, or at least silent. I don't say off, actually, silent, because I'd love everybody to tweet. I don't know if we have, just #Milner will do. For those of you, I'll be tweeting. So, it is being webcast and recorded, so if you ask questions later, you should know that that is going out live. And there are no planned evacuations, so if there's a fire alarm, run like hell. Actually, no, walk calmly over here, and someone will tell you where to go. Okay, enough. Let's get on to the science and to the winner of our award. First of all, to tell you a little bit about the award. So, the Royal Society Milner Award is named after Robin Milner, an old friend of many of us in the audience. It is supported by Microsoft Research, to whom we are very grateful. He was, of course, associated with Microsoft for much of his career. And it's given annually for outstanding achievement in computer science by a European researcher. The winner of the award receives a medal and a personal prize of £5,000, and I've got the cash in my handbag, okay? No, you get the cheque some other time, but there is prize money for this. And the winner is invited to deliver a public lecture on their research at the Society and should be an active researcher in the area of computer science. So here we are at the public lecture for the 2016 winner, Dr. Xavier Leroy. He was awarded the 2016 Milner Award, and the citation is for exceptional achievements in computer programming, which includes the design and implementation of the OCaml programming language. Dr. Leroy, Xavier, is a senior research scientist at Inria, where he leads the Gallium research team. His research focuses on programming languages and tools and on the formal verification of software using program proof and static analysis. He is the architect and one of the main developers of the OCaml functional programming language and of the CompCert formally verified C compiler. He graduated from École Normale Supérieure, gosh, it's testing my French, not very good I should add, in 1991, and received his PhD in computer science from the University of Paris Diderot in 1992. So, without further ado, let's welcome Dr. Leroy to the stage.
Well, thank you very much for this kind introduction. Can you all hear me? Okay. And, well, thank you very much for this award. I mean, it's an immense honor for me. And it's even more of an honor because it's named after Robin Milner, who was kind of a spiritual father to me, and, well, one of the pioneers and founders of my area of computer science. Many times in my research work, I had the impression to walk down paths that Milner blazed 20 years before, and we will actually see an example in the talk. So yes, let's remember Milner as one of the most creative and inventive computer scientists of all times. All right, so what I would like to talk about tonight is an obsession of mine that's been with me since I started programming as a teenager. I think it is an obsession that I share with some people in the audience. Obsession with the perfect piece of software, the perfect computer program, the one that does exactly what it should do, no more, no less, every time, with perfect reliability and forever. The kind of perfection that you can get from mathematical definitions, which software is, to a large extent, or from philosophical concepts. And still, everyday experience shows that software is very much imperfect, right? So for instance, software crashes all too often. And so that's the so-called blue screen of death that the Windows operating system displays when something goes very, very bad. And you spot it in various places, like on a highway leading to Paris, on a billboard in Las Vegas, on a metro station in Manhattan, at Heathrow Airport, at the opening ceremonies of the Olympics in 2008, and even at a concert of the Nine Inch Nails band. But, well, that's not too bad. I mean, we just reboot and upgrade, and life goes on. But sometimes software has security holes. So instead of crashing, it can be exploited by a malicious attacker to do bad things. So what you see on your left is a modern high-end car, and as shown on the right, it has many functions where software is involved. For instance, braking for anti-lock, throttle for cruise control, but even steering for parking assistance. And it also has a radio unit with, in particular, a GSM connection and mobile phone connection to call for rescue in case of an accident. And all those things are connected through a bus called the CAN bus, CAN bus. And so to make a long story short, those two security experts, Milner and Valasek, exploited security holes in all those pieces of software to not take remote control of the car, but at least being able remotely to interfere with the brakes and the steering, putting the car in the ditch. And that is getting a little scary. And what is really scary is that sometimes software kills. So there are a few documented cases of human death caused by software errors, mostly in the medical equipment world. So to your left, it's the Terac-25 radiation machine, radiotherapy machine, which caused the death of at least 3 patients following massive overdose that the software should have prevented. And on your right, it's a baby monitor. It monitors the heart rate and breathing patterns of newborns to warn in case of in case of sudden infant death syndrome. And for one particular make and model, there were several cases where the baby died, and the log of the machine says that the alarm rang, and nurses and family who were in the room say that nothing was heard. And so we don't quite know what happened. Probably, well, my guess is that the software crashed just before actually ringing the alarm, but who knows? All right, so that's a pretty grim picture of software that I've painted. So let me try now to be a little more optimistic and show you an example of a family of software systems that are actually extremely reliable and get close to this perfection I've been dreaming of. So I'll take my example from the world of airplanes. There are similar examples in other areas like railway or nuclear power plants as well. So what you have here is an airplane, and how do you control an airplane? By moving those various surfaces, flaps, ailerons, spoilers, droop, elevator, rudder, and a few others. And traditionally, those surfaces are connected to the stick and pedals of the pilot through mechanical links, or more often than not, hydraulic links. But those hydraulic links are heavy, they need a lot of maintenance, and they are kind of fragile when there's, for instance, shrapnel because an engine explodes. And so in some newer airplanes, those are replaced by a so-called fly-by-wire system, where there's an actuator close to every control surface, and that takes order through basically a local network from a fly-by-wire computer, which takes input from the pilot's stick and also from the autopilot and other sensors. And so that's not a new idea at all. So the first fly-by-wire airplanes appear in the late 50s. So those were the first supersonic fighters, like the Avro CF-105, because basically you cannot fly supersonic with only mechanical control, so it's extremely hard. But those were flown, I mean, the computer was an analog computer, okay, it didn't really have software. And the first passenger airplane with fly-by-wire system was the Concorde back in 1969, again because it is supersonic, and again mostly analog system. I've been told there was one digital computer on the Concorde with 4 kilobytes of code, and I have no idea what it does. And so the first passenger airplane with real fly-by-wire software, a fully digital system, is the Airbus 320, which appeared in '84. And at that time, that caused quite a bit of concern and consternation. For instance, some people were talking of computer-aided disaster. It's a pun of computer-aided design. Okay, so computer-aided disaster. The one in French is pretty good, I think. It says the complexity of embedded software threatens aircraft safety, which might be still true today. But actually, the disaster did not occur. So Airbus was expecting one major problem with the software every 10 million hours of flight. And this particular plane has flown, I think, 50 or 60 million hours of flight without any major problem due to the software. So they are crossing their fingers. And then Boeing followed suit with a 777. And nowadays, so all the big aircraft from Airbus and Boeing are all fly-by-wire. All right, so what does it do, this fly-by-wire system? Well, first and foremost, it executes the pilot's commands. That's its main purpose in life. And then it has some flight assistance. So you have some names here, like high angle of attack protection and so on. And the idea is to keep the aircraft within a safe flight envelope. So for instance, an aircraft that climbs too much loses speed and eventually stalls and falls. Okay, so that's not good. An aircraft that dives too much gains speed, and it can get supersonic, which is extremely bad if it's not a supersonic aircraft. So likewise, an aircraft that banks too much on the side will get into a spiral, okay, and crash also. And so the goal of the software here is basically to prevent that by acting on the control surfaces. A little bit like anti-lock brakes, okay, where the brakes get out of control for a while, okay, just so that the car doesn't skid and stays controllable. All right, so that's one big function. There's also some function having to do with fuel economy, trying to minimize aerodynamic drag. And for that, you need to fly the plane close to the point where it is unstable. Okay, and software is very good at that. Some more amusing things. It can also help with active damping of some oscillations. So this is an oscillation mode called a Dutch roll. And it's a natural oscillation mode of aircraft, and pilots tend to make it worse when they try to compensate for it. But software is very good at just moving a little bit the surfaces to damp that. Okay, so that's the kind of thing it does. And now, how does it look as a program? So typically, it's a two-part software with a minimalistic operating system, basically a part that is familiar to the computer scientists in the room, often written in C, which handles boot, self-test, communication over buses, static scheduling of periodic tasks. It's generally handcrafted. Sometimes they use off-the-shelf real-time operating systems. But most of it is actually control command code. And I'll show some example in a minute for those computer people in the room who don't know about that. But it's basically discretized differential equations. A few more facts. So in general, it's hard real time. Those differential equations must be clocked precisely. Okay, otherwise, the mathematics are not quite right, and we are not quite sure what happens. It can be pretty big, a few hundred kilo lines of code. But most of it is generally generated from higher level notations like scalar Simulink. And there's a lot of asymmetric redundancy in the implementation. There's usually two versions of the software, the primary and the secondary. The secondary is simpler, and its main purpose is to bring the plane back to Earth. Then each is implemented in at least two different ways, and then run on different computers. So there's also hardware redundancy. Okay, so a few words about those control laws, because, well, that's something I learned about quite recently. So it's basically a mathematical relation between the action that needs to be performed in your system and the error, which is the difference between the desired state and the current state. So for instance, this is the hello world example, it's a so-called PID controller, where the action is proportional to the error, and proportional to the integral of the error, and proportional to the derivative of the error, and if you choose the coefficients right, you get some pretty good controls and responses like the one shown here. And what I find fascinating about those things is that they predate computers by several decades, okay? And for instance, you have mechanical implementations of those. So this one is pneumatic with compressed air, and it doesn't make any sense to me, but never mind. You have analog electronics implementation. So this one makes sense to me. So it's just one operational amplifier, 2 resistors, 2 capacitances, and that implements the PID controller. That's the kind of circuits that flew the Concorde, right? But as elegant as it is, analog electronics is still vulnerable to noise, electrical noise, and also to aging of components. And so the current favorite to implement those control laws is in software. Basically, you discretize the differential equation, and then you run it every dt time interval, updating the various parts of the formula. Okay. But actually, the engineers the control engineers who develop those kind of things hate to write it this way. And they like block diagrams. And there are whole languages and systems that are dedicated to that, like Simulink, Skate, Psychos, etc. And basically, those look like idealized circuits, electronic circuits, right? Except that it's not really tensions and currents that flow here. It's more like sequences of numbers. And the various components are just mathematical functions like multiplication, integration, derivation, summation, and feedback loop. And the beauty of those diagrams is that, well, the engineers feel comfortable with them, but at the same time, they can be used to generate executable code. So in the case of Skate, this is actually a graphical syntax for a real programming language called Lustre, which is basically a language where you can write recursive equations that define a time-indexed series using some temporal operators like followed by and previous. So I'm not getting into details here, but just to illustrate that methodology, which I think is very nice. So starting with the control law, instead of just discretizing by hand as recursive sequences and then hand coding into C, you can model as a block diagram, which is a syntax for some Lustre code, whose semantics is exactly the recursive sequences and from which the C code is automatically generated. And that's a very nice example of a domain-specific language. All right, but let me come back to these fly-by-wire systems and what goes on in the aircraft. So before an aircraft can fly with passengers, okay, it has to be certified and so get a green light from certification authorities like the European Aerospace Agency or the FAA in the US. And for that, they follow regulations called the DO. So for software, it's DO 178 for airborne software systems. And it is a pretty demanding standard that describes the design and development process, which should be fully documented, and demands rigorous validation at multiple levels, from design to the actual onboard computer, involving reviews, so qualitative analyses of what's going on, analyses which are more quantitative, like what's the worst case execution time for this piece of code, and a whole lot of testing. Okay, really amazing quantities of testing with some pretty clever testing techniques. We'll see some of them. And a recent development, which is the use of formal verification tools, and that will be the second part of my talk. But a few words about testing. So like everyone else, I start with unit testing. Okay, I take a little bit of code, like this max function in your mathematical library. You give it some values, and you check that the results make sense. Seems like they make sense, except when one of the arguments is a special floating point number called not a number, in which case it doesn't make any sense, but well, beware. Beware of not a numbers. Then they do integration testing, which is basically taking the onboard computer and plugging it into a bunch of custom electronics that simulate the bus and some of the things that come from the sensors and some of the things that go to the actuators. So that's already pretty cool. And then the last step is really impressive. It's called exploration on an iron bird. So the iron bird, I don't know if you can see it very well. It's kind of the skeleton of the final plane. And it has all the actuators, all the cabling, all the computers, okay? And it's connected to a simulator cockpit. And the only thing that is simulated are basically the sensors, okay, like weather sensors. And then there's a test pilot in there, and whose purpose is to explore how the plane reacts, okay? And that works so well that so in the end, they still do test flights, and that's where you see nice pictures in the newspapers, and that's where they get some very good public relation. But the test flights are more and more successful, okay, and they take less and less time. So that's some pretty impressive testing, I think, at least from a computer scientist / programmer viewpoint, where I admit I often skimp on testing. So that's pretty impressive, but still, there's the emergence of this new technique, tool-assisted formal verification that I mentioned, and that I'm going to talk about now. All right, so the idea of formal verification is to go beyond testing, in particular beyond this nasty objection of Dijkstra in '72. I said that basically testing cannot show the absence of bugs because in general there's infinitely many states of your system and you cannot test all of them. So formal verification is trying to go beyond that limitation using mathematical techniques to verify and possibly infer properties that do hold of all possible executions of a program, even if there's infinitely many. And so it is used in a few industrial contexts, like the aircraft industries, the railways industries, the nuclear industry I mentioned already, for several purposes, typically to obtain independent guarantees besides testing. I mean, in those kind of industries, when something is important and it is true for two different reasons, it makes it truer. Okay, it's very interesting to have two independent reasons why something is good. Formal methods can also be used to obtain stronger guarantees than obtained with testing, but that's a slippery argument. I mean, you will never get an airplane manufacturer to publicly admit that their testing is inadequate. Okay, never. Maybe in private, but. And sometimes it's used to save money because it can replace, for instance, some unit tests that are actually quite costly to develop and administer. So sometimes money talks and pushes towards the use of those mathematical techniques. But let me show you a little more what they look like. So there are several, static analysis, model checking, program proof, deductive verification, and even proof assistance there, which differ in basically how rich, how complex are the properties they can check, and how much automation you get. Okay, so for instance, static analysis will infer some pretty simple properties of one variable, like a variation interval, or several variables, like a linear inequality, but they will do that automatically and on a fairly large scale, up to 1 million lines of code. Model checkers are still pretty automatic, but a little less, and focus on showing that some bad states are not reachable, or basically showing focus on reachability problems. Deductive program provers can actually prove full correctness, so really strong properties about your programs, but need a lot more help from the user in the form of logical assertions like preconditions and invariants and postconditions. And then at the bottom, you have proof assistance, where most of the proof is done interactively, done by a human, but then you have the power of full mathematics. And let me show you that at work on an example. Okay, so that's a little program written in pseudo Java syntax that computes the first n prime numbers. Okay, so you give it n, and at the end it should fill this array with n prime numbers. And the algorithm is familiar. It's a sieve of Eratosthenes. Okay, you try successive numbers and you strike out those that are divisible by primes you already found. Okay, so that's a pretty simple piece of code. And now if you run a good static analyzer on this, it can show, well, it can infer some properties of your loop index variables, j and I. And from those inequalities here and there, you can deduce that all those array accesses are safe, are within bounds, which is already pretty good. So you know that this code is not going to stop on an array index out of bounds exception. Now, if you use an automatic program prover and you give some annotations in this program, it can actually prove partial correctness. Basically, that if the program finishes, if the program terminates, your array contains the first n prime numbers. So you need to teach the program prover some simple axioms about primality, divisibility. You need to provide logical assertions like this loop invariant that says basically that at every point of this loop, from the first I element of the array contain prime numbers, and all prime numbers between 2 and m are in this array, and there are no duplicates. Well, the array is strictly increasing. But still, you can manage. Then you may wonder about termination. So full correctness, can I prove that it always terminates? Well, that's harder because it depends on the fact that there are infinitely many prime numbers. If there were only 10 prime numbers and you ask for 11 numbers, it would loop forever. Okay. So that's a kind of higher mathematics that are harder to exploit in an automatic program prover. And then there is Knuth's cunning optimization. Okay, so this example is actually from one of the first chapters of The Art of Computer Programming. And Knuth remarks in passing that this test, j less than I, is actually redundant with this other test there and can be omitted, and the program will run faster. And Knuth says that it's not obvious why, and indeed it is not, because it depends on a fairly deep result of number theory called Bertrand's postulate, which is that between n and 2n, there's always at least one prime number. Okay? And so that's a non-obvious result. So it was proved for the first time by the great Chebyshev. And then the modern proof is due to the great Erdos. And if you really want to prove that code with that optimization, you will need higher mathematics, and you will need a proof assistant, such as a Coq system. And fortunately, there is a Coq proof of Erdos proof due to my colleague Laurent Théry. But still, as you see, a little optimization can go a long way in terms of complexity of verification. All right, and so I mentioned that those tools are starting to be used in industrial settings. So here are some success stories for avionics code. So at Airbus, they use two static analyzers. One is called WSET and infers worst-case execution time, so precise time bounds over the code. The other is called Astray, works at the level of the C code and shows the absence of runtime errors, like out-of-bound accesses, or integer or even floating point arithmetic overflows. They also use a program prover called Caveat. Basically, so Astray is run on large pieces of code, up to 1 million of lines. Caveat is run on small libraries, okay? But as a replacement for unit tests that are quite painful for those basic library functions. And so they even call that unit proofs, which is a pretty cool concept, I guess. And at another aircraft equipment manufacturer, Rockwell Collins, so they have a very nice tool chain that works at the level of Simulink or SCADE models, reactive models, and that combines model checking with program proof. So it's really nice to see those tools starting to be used in anger. And they are also starting to be used in other areas of computer science, like, for instance, for the verification of systems code, like operating systems and the like. So, for instance, at NICTA in Australia in 2009, they completed the verification of a full secure microkernel. And even though that's a relatively small piece of code, 8,000 lines of C code, it's a very complex piece of code, and the proof is huge and took 20 years of effort. But they managed using mostly proof assistant. But more recently, there has been some interest towards the verification of file systems, which is another component of operating system, which is quite important, and in particular showing that the file system remains consistent even in the presence of things like power outages or unexpected interruptions. And the latest work in this line that was recently published, they actually managed to do a fully automatic verification of a realistic file system using some custom tool that they developed for that purpose. So they're also making some progress towards making those verifications more usable. All right, and so now let me get to the final part of this lecture, and where I will talk a little bit about my own work in this area. But first, I would like to to draw your attention on the trust issue. So, okay, we have software verification tools, and that can help building confidence in software. But now, how confident can we be in the guarantees given by those tools? And there are basically two risks here. One is called the unsoundness risk, and it concerns the tools themselves. So maybe by error, by mistake in implementing the tool, or maybe even sometimes by design, the tool can be optimistic and say, yes, that program is fine. And even though there is an execution path at runtime that can cause bad things to happen. All right. So that's risk number one. And then risk number two, which is the one I will talk most about today, is more insidious. It has to do with the fact that most of those verification tools actually operate not on the executable code that actually runs in the aircraft or in the embedded system, but on source code or even on models. Okay? And there's quite a distance between those models, the source code and the executable. From the model to the source code, it's generally automatic code generation. And for the source code to the executable, it is compilation with a compiler. And in both cases, miscompilation can occur. So miscompilation is basically you give a correct program to your compiler, for instance, and because there's a bug in the compiler, it generates wrong code. Okay? Code that may crash or that may compute the wrong result. And so miscompilation happens. So it is documented in the literature. For instance, in '95, Nullstone, which is a conformance test suite for C compilers, isolated defects in the way integer division is compiled, so really a basic operation, in 12 of 20 commercially available compilers that they evaluated. Okay. So have we made much progress since then? Maybe not that much. So in 2008, ID and Reger from the University of Utah did testing of many C compilers for another aspect of the C language, so-called volatile variables, which is important for systems code. And again, they found miscompilation issues with volatile variables in the 13 production quality C compilers they tested. And then they generalized, the same people from Utah University, generalized their techniques, which is their testing technique, which is based on random generation of interesting C programs, with a C-Smith tool, which they used to test a number of compilers. And so again, every compiler they tested was found to crash at compile time, which is unpleasant, but not that bad. At least the programmer is aware that something is wrong. But also to silently generate wrong code when presented with valid input, which is miscompilation and which is kind of a concern. So why is it so hard to compile? Why is it so hard to generate correct code? There are several answers to this. So one is sometimes the source language is not very well specified, so there's possible misunderstanding between the programmer and between the compiler writer about what a correct program is and what correct code for a correct program is. But most of the time, the problems come from the desire to improve performance. So it's called optimizations, okay? And so many compilers actually try to rewrite the code you give to them in order to make it run faster, okay? And it's called pretentiously optimization. It should rather be called improvement, but well. And so let me show you the kind of distance some compilers can go in trying to optimize things. That's an experiment I did when I started working on this topic about 12 years ago. So this is a C function that computes the dot product of two vectors of length n of floating point numbers. Okay, and it's really a transliteration of the mathematical formula that defines dot product with a loop that computes the sum of the product. And then so I compiled that with a good compiler with full optimizations on, and I looked at the generated assembly code and I couldn't make any sense out of it. It was really big for such a small function, and it made absolutely no sense. But well, that's assembly code, it's not a very friendly language, so then I spent half an hour manually decompiling it back to C code, try to understand. And I got this piece of C code, which is still huge, which is still very hard to understand. And after a while, you notice something that is a loop. Aha. You see there's a goto here that branches back there, so that's a loop. So maybe it matches the original loop. Well, to some extent, because the compiler first chose to unroll the original loop by a factor of 4. So every iteration of this loop is doing the job of 4 iterations of the initial loop. Then it applied the technique known as software pipelining, whereas the current iteration here does the 4 additions for the current iteration, and then it anticipates the 4 multiplications for iteration I+1, and then it anticipates the 8 memory loads for iteration I+2. And so by anticipating those computations, it gives more time to the hardware to actually finish those computations. So you're increasing instruction level parallelism. You're taking better advantage of the hardware capabilities. Okay, but now you may wonder, what does all the rest of the code do? Okay, well, it's handling special cases. Because the software pipeline is like a pipeline. It needs to be primed, so the first iteration is special. Then it needs to be drained, so the last iteration is special. And because of that, it doesn't run if the number of iterations is too small, in which case another version of the loop is used somewhere in here. And then, because of this unrolling by a factor of 4, there are also n modulo 4 iterations of the loop that remain to be done in the end. Okay. So in the end, this code does this, and it runs maybe 2 or 3 times faster than the naive assembly code you may have written by hand. So the compiler did a great job of optimizing and taking advantage of the hardware. But does this code still compute dot product? I have absolutely no idea. Okay. So how to address this miscompilation risk? Well, there are best industrial practices, which is basically more testing, okay? More reviews of generated assembly code. And as we just saw, it's impossible for optimized assembly code. So they turn optimizations off until they can review. And, well, those kind of stopgap measures. But there's a more radical solution. Why not formally verify the compiler itself? Okay? The compiler is a piece of software. It's a complicated piece of software, but it has a simple specification, which is that if compilation succeeds, the generated code should behave as prescribed by the semantics of the source program. So basically, it's let's preserve the meaning of the source program. And let's try to improve performance maybe, but let's preserve the meaning. And maybe we can formally verify that property by applying formal methods to the compiler itself. And if we have that property, we also have a very nice corollary, which is that the safety properties that we have verified at the source level using static analyzers or other tools will carry over to the executable generated code. Okay. And so that justifies, in a way, this practice of using tools at the source level or maybe even at the model level. All right, so let's formally verify the compiler. And well, that's a great idea. It's an old idea too. So it appears first in the literature in 1967, a famous paper by John McCarthy and James Painter. The first paper to notice that there is something interesting to be proved mathematically about a compiler. And then they proceed to do a proof for the simplest compiler they could think of, which is compiling arithmetic expressions to stack machine code. But they say that their ultimate goal, their techniques are intended to serve as prototypes for the more complicated task of proving the correctness of usable compilers. So they already had pretty big ambitions. And only 5 years later, Robin Milner and his colleague Richard Weirauch from Stanford University at the time mechanized this proof of McCarthy and Painter. So basically they translated it in a mathematical language that is understandable by the computer and where the proofs can be checked by a proof assistant. So that was one of the very first proof assistants, Stanford LCF. And so that's one of the very first proofs that were verified with an interactive proof assistant. And again, they say that, well, the real goal is to compile correctly an algol-like language, but they only do arithmetic expressions, but they anticipate no difficulty with the remainder. It was a little bit optimistic. Even today, there is still no full algol compiler that is formally verified. And then it prompted quite a bit of work in the late 80s, starting in the late 80s. So that's the next 100 papers on compiler verification, as compiled by Maulik Dave, his bibliography. And I've put some colors for some projects that are particularly notable. And then let me talk about my project in this area. So it's the CompCert verified C compiler. A project that I started with some colleagues, especially Sandrine Blasi, who is now at University of Rennes, around 2005, I would say, 2004, 2005. So we set out to develop and prove correct a realistic compiler, usable for critical embedded software. So by realistic, we mean that the source language is one that is typically used for critical embedded software, namely the C programming language, even though it's a fairly ugly and complicated programming language, but that's what people use. Likewise, the target language is not a stack machine or an idealized processor, it's real processors used in embedded systems, like PowerPC, ARM, and x86 currently. And also we set out to generate reasonably compact and fast code through careful code generation and some optimizations. So one thing to note is that we are not trying to take an existing compiler like GCC and proving it correct. That would be hard because GCC is huge, million lines of code, and was never written with the need of a proof in mind. So instead, we develop our own compiler from scratch along with its proof. And so that's the formally verified part of the compiler. So we start with CompCert C, abstract syntax for our large subset of C. And we go to assembly languages for our 3 target platforms, going through a number of intermediate languages of progressively lower intermediate level. And so we have a number of passes of code transformations. So some of them are just, code generation passes, simplifying, expressing high-level constructs in terms of lower-level constructs. And a few passes are optimizations, trying to remove inefficiencies, improve performance. And so that might look impressive if you're not familiar with compilers. Actually, it's not. A real compiler like GCC has maybe 100 passes. This is only 15. But what is new here is that each of those languages, source, intermediate, target, has a formal semantics that defines mathematically what programs mean. And each of those passes, each of those arrows, is proved to preserve this meaning, this semantics. Okay? And so does the whole compiler. And so to conduct that proof, and to write the specs and to conduct the proofs, we use machine assistance, because otherwise done on papers that would just be too big and too boring, and no one would ever review that proof. So we use the Coq proof assistant to provide us with machine checking. And so this is one of the final theorems. I'm not sure I have time to really read that, but it's in actual Coq syntax, so just to show you that it's not too unreadable. Basically, trans-C program is a function that composes all those passes. And what it says is that if you feed it some program P in C, and trans-C program doesn't report an error but says OK, and then gives you TP, which is a transform program in assembly language, then any observable behavior of your program TP, according to the assembly semantics, matches or improves over a possible behavior of your source program P according to the C semantics. So what we observe here are things like termination, non-termination, and input-output operations, so traces of I/O. And what we show is a refinement of those behaviors. So those behavior, we can have reduction of internal non-determinism, choose one evaluation order among the several allowed by C. And we can also have replacement of runtime errors by more defined behaviors. For instance, there was an integer division by 0 in the source, but it's been optimized away. Okay, so the generated program will crash less often if you want. Okay, and so a few patterns proof patterns that we use. So for every pass, we have a choice between actually formalizing the transformation, the code transformation, and proving it correct for all possible inputs, proving semantic preservation for all possible inputs. But there's also another approach based on translation validation in the style of PNUELI, where the transformation is not proved correct, but at every run, its input and its output are fed into a validator that tries to prove semantic equivalence. And so if we just prove the soundness of a validator, then we are good. We have correctness guarantees that are as strong as in the soundness guarantees that are as strong as in the other case, but perhaps with less effort of proof. And then you can mix and match both approaches. Another point to note is that we use the proof assistant also as a programming language. So the verified part of the compiler are programmed directly in code specification language. We use pure functional style. We use monads to handle error on mutable state. We use purely functional data structures. And then we get mathematical objects that code can directly reason upon without the need for a program logic. But still, we don't lose executability because we can generate executable camel code from there. So I think it's a nice illustration of the power of purely functional programming when it comes to writing and proving a program. All right, so yeah, I see I'm running out of time, so let me just finish quickly. So this is the whole CompCert compiler. As I said, not everything is proved. So this is the part that is proved and then extracted to camel. And we put it together with some other tools that are not yet proved, like a preprocessor, an assembler, or a linker. And among the years, we've been moving some part from this non-proved part to the proved part, and we will keep doing that for the forthcoming years. We can benchmark the performance of the generated code, which is competitive with the GNU compiler, the GCC compiler at optimization level 1, which is not very high optimization, but still pretty good. So the performance is decent, not great. And the beauty is that we get a tangible increase in quality. So remember those people from the University of Utah who are doing random testing of compilers? Well, they also run their tool on CompCert, an early version of CompCert. And they threw 6 CPU years at it and couldn't break CompCert. I mean, they couldn't exhibit a miscompilation issue. They exhibited many cases where CompCert would reject or refuse to generate code. And so they conclude that, well, that proof has some tangible benefits for compiler users. OK, and so to conclude, is software perfection within reach, after all? And let me prudently say perhaps. But I think at the minimum, we need a lot of things that are rarely found all together in the same project. We need mathematical specifications. Control command is very nice for that. Okay, there's all this mathematical background. What are the mathematical specifications of a web browser, for instance? I'm not quite sure. We need appropriate programming languages, even after all those years. So we saw how Scale is good for control command. I think for many other application areas, we still haven't found the right domain-specific language. We need really serious testing. And I say serious, it's of the airplane kind, okay, not of the computer programmer kind, who tries with 5 different values and says it's okay. We also need formal verification, and tools like and techniques such as static analysis, model checking, program proof can contribute a lot. We need trustworthy tools. So this CompCert compiler is an example. Another project I've been working on and I couldn't mention is Verasco, which is a static analyzer that's been proved sound using the same techniques as CompCert. We need theorem proving as a kind of backend for many of those verification efforts. Interactive, like CoreHOL, or automatic, like DET3. And I think we still need further research, in particular to make that more scalable and more accessible to the general public and not just a few elite engineers from Airbus. But there's much hope, and I thank you for your attention.
I've got lots of questions, but I get a chance to ask him later. So over to you. We have mics. Who would like? We can do about 15 minutes of questions now. That was a great lecture, really, really fantastic. So the gentleman down here. So could you tell us who you are when you ask your question?
Sure. Hi, my name is Ali. I'm from a company called TestSoft. You can guess what it does. Great lecture, thank you very much. So my question is, and I could be wrong, but the assumption was that the hardware was fixed. In the world of FPGAs, how does this hold?
Indeed, so I didn't talk about hardware or hardware verification, but actually the same kind of problems occur. Okay, sometimes hardware is buggy, or perhaps less often than software. And again, some of those formal verification techniques I mentioned have been applied to hardware as well. In particular, model checking is routinely used at Intel, AMD, and other big players, and they also do some proof, mathematical proof. So for FPGA, I guess we could at least conceptually extend the verification all the way to I don't know, the netlist or whatever form is actually implemented in the FPGA. I don't have personal experience with that, but I know some people who work theorem proving have a lot of experience with hardware verification. Does this answer our question?
And have you got one as well? We'll prime you up, yeah. So, what's gentleman there? Is there another? I can't see the mic.
Yeah, she's here.
Yeah, yes, gentleman there with the beard. Easy one to do. Okay, so you go at the back there, and then, yeah. I can't see you. I'll come up here.
Hi, Andrew Fitzgibbon from Microsoft. You mentioned a few times that a good source of broken code is code that programmers have tried to speed up. I can imagine twisting this to, I write my prime program as dumbly and inefficiently as I like, and the machine automatically finds me the Ziva Eratosthenes and the J less than I optimization.
Yes, well, it's an old dream, but so it's called program synthesis. Well, in the extreme, it's program synthesis. Okay, you just give a specification of what you want, and the tool tries to find an executable and efficient version of a program that will compute it. So it's a technique that has made some progress recently because, well, a lot of synthesis problems can boil down to actually solving logical formulas, okay? And so you get some leverage from those automatic provers I mentioned. You said the technique is still far from practical. I mean, you can synthesize some non-trivial pieces of code with that. I'm not quite sure you can synthesize this Eratosthenes sieve I showed. And then, well, yeah, maybe what you had in mind was more like taking an optimized and non-optimized version of the same program and trying to prove an equivalence a posteriori. Again, there are some cases where it can be done relatively efficiently or automatically. And I think, for instance, that this file system verification work is a little bit like this. So they have some logic that automates the reasoning of the kind, oh, but if it crashes now and restarts later, will it still be consistent? Okay, so it's a way of reasoning on a simple code with a simple model and actually tell things that hold of a more complicated code and more complicated model. Okay.
So we were here next.
My name's Tom Lake. My question is about specifications and standards. So the first question, did you have a lot to do with the C standard to get it into usable semantics?
Yes.
And then looking wider, when you look at the world of specification, for example, I've done some work with the SIP protocol standards, the RFCs, you know, IETF, RFCs. So these are documents which are very far from any formal sort of standard. So I wonder what your views are on protocols and standards.
So indeed, after a while, you realize that perhaps the main difficulty is getting the right specifications first. Okay, and after that, the verification is a lot of work, but it's at least you have an idea of the process. So getting the right specifications is quite hard, and indeed, for the case of the C language, Sandrine Blazy and I, we started by saying, okay, we've been programming in C for 20 years. It can't be really hard to write formal semantics, right? And actually, it is pretty hard. And even though we don't treat the whole C language, we purposefully specify more things than what's in the standard, etc., etc. And since then, there have been other, or before and after, there have been other brilliant attempts at really formalizing the C standards, like Michael Norrich's PhD thesis, and more recently Robert Kreber's PhD thesis. So indeed, C is an example of difficult formal specification. This said, for instance, I'm working with some people to formalize and verify a Lustre to C, a code generator, and here, I mean, a language such as Lustre is much more elegant in its semantics, and the formalization is much nicer. So indeed, getting the specs right is tough, and indeed, and then you also need to validate them. Okay, so it's good to have a way to test your specs, so make them executable, have test suites that can be run against the specifications, just to make sure that you've captured the right thing.
Thank you.
Thank you. I really enjoyed your talk, and I noted your last question your last slide says we need more research. I've got two questions. One's a personal question and one's a general question for everybody here and in fact for the whole world. My personal question is, I work in medical device software and it is rubbish. It kills patients, nurses go to prison and nurses commit suicide. It is horrific, and I'd love to talk more about it, but for the question, I've just had a personal question, I've just had a research proposal rejected. A referee said, fixing bugs is not research. So what would your response to that, be?
That's tough.
And then I'm sure you can remember that question. The second question is for all of us, if intelligent people believe fixing bugs is not research, okay, what are we going to do about the world? In Britain, because I've been involved in expert witnessing with clinical software, the Criminal Justice Act says there is a presumption in law that IT works at the material time. In other words, in court, IT works, and the judge won't give you access to the software because it works. Mm-hmm. Right? So my referee says fixing bugs is not research, but the world we live in is IT is perfect, so why do any work at all? We've got to fix both problems, I think.
Well, yeah, I'm not sure I can add much to that. Only that, I think at some point, industry also has to embrace those formal methods, okay? And maybe that's what your reviewer meant. That maybe it's time for big companies to invest some of their considerable funds in more formal verification. So I'm not going to give names, but I mean, among the big ones, a few have a big investment in formal verification, and others don't really care. So indeed, at some point, we academics, I mean, it's fun to hone our skills and tune our tools and so on real software, and I enjoy that. But at some point, we have to hand over to bigger teams and people who are closer to the applications and the customers. So maybe that's what your reviewer said in very bad way, I agree.
Chris Bishop from Microsoft Research. First of all, that was a superb lecture. I think it was a case study in clear communication. It was wonderful. I loved it. My question is this. So increasingly, we're seeing software that's constructed not by compilation of handcrafted code, but rather by learning from data. And of course, the learning code itself may be subject to formal verification. That's wonderful. But of course, the end result depends on this statistical process of the data itself. So is there any prospect for bringing more than empirical testing to that domain?
Indeed, I really don't know, and I think this is going to be one of the big puzzles now that, well, statistical techniques, machine learning are getting everywhere, and now that Google has self-driving cars that drive on machine-learned laws, right? So indeed, I tried to think what could we do with one of those cars to prove some safety properties, and really I'm not quite sure. So optimistically, you could separate your software into, well, one that tries to drive and one part that just monitors, okay? A little bit like the ABS brakes or the flight assistance in the airplane. The software doesn't fly the plane, but it prevents bad things from happening. So maybe we could do that and just verify the controller, the monitor. But it's not obvious what the monitor would look like. Okay, if the monitor detects something dangerous, what do you do? I mean, just bringing the car to a safe halt is an extremely hard driving problem already. So it's unclear what to do. And then there are also some horrible societal aspects. I mean, you could say cynically, but that's probably right, that people are very bad drivers already. People drive so badly that even a buggy piece of software will drive better and kill fewer persons. Okay, but if it's that true, are we ready to accept, being killed by software just because we get killed less often than by humans? That's really a nightmare. Okay, and I have no idea what we will do with that kind of questions.
I think. Oh, I can see two hands going up. All right, last two questions, and I was going to close it there, but I won't. So. The younger man, and there's a gentleman in the middle at the back. Risha, can you get there? And then we'll close it. Right, okay.
Hi, Louis Maddox. I work at Benevolent AI in neurodegenerative drug discovery research. You talked about making this accessible. So there's a few things about that. So I personally know of the Julia language has people working on these sorts of form verification tools. That has been mentioned so far. As regards self-driving cars, I know there's a big community in London of people who are sort of starting to train themselves to what, in recent announcements, seems to be about to become a career move for some people, effectively. And what sort of tools would make these principles sort of accessible to those people? And to address the issue of learning from data, which has been mentioned, machine learning models have been trained on, for example, Grand Theft Auto, car driving, as well as real-world examples. And how do you... Sorry, I just wanted to mention.
I'm sorry, I didn't really understand your question, so maybe we'll take that offline.
Okay.
John Nordwall. Have you got a problem with proving the completeness of the failure analysis in your overall safety problem? And it seems to me that new challenges like the car driving one, where the software engineer writing the driving program does not think in the same way that the pedestrians and the surrounding people do, illustrates a desire for diversity in the analytical process. So your testing program, for example, should not necessarily be, or not entirely be done by people from the industry that designed the program. Mm-hmm. Take it to the local poly and let the students try to crash your plane.
All right. So quick answer to your first question, and then I'll come back to the second. So the first question was about completeness, and indeed, in general, we sacrifice completeness in those techniques. Okay. We are happy if the technique succeeds in proving one program or the program we are interested in. There's in general no guarantee that it will prove all provable programs, if you see my drift. For your second point, so indeed, I think in an ideal world, some of this testing or even some of this formal verification would be done by outsiders, by authorities, by consumers associations, and maybe we will come to that at some point. Right now, quite often you still have to trust the manufacturer and that the manufacturer adheres to the laws and the regulations and the code of conduct. But there's one case where what you describe already happens. It's for security. You have lots of hackers who try to find security holes in your software, okay, and for free. So we already see some of that at work.
Thank you. So,
Thank you.
now wait, hold your applause, because I now have to present you with, excuse me,
Go ahead.
they're down here. I was looking for them earlier. Okay. So I'd like to say thank you for the lecture. It was, as Chris said, a wonderful example of how to give a lecture on a very complicated subject that could appeal to anybody. There's so much in the world that's going to need this type of approach. And as you were asking your question, I think, so your question also was a bit about in the future, we won't just be worrying about verifying the software, we'll be verifying the data as well. I think that's going to be a huge matter going forward. And I'm thinking of, we've been talking about smart cars and killing people. With the coming internet of toasters,
It's a good one.
we're going to have smart houses and smart cities. Think of the house that kills you or the city that kills a population. These are going to be huge issues going forward as we build more and more complex systems, and your work and the work of others like you is going to be really important in that. So thank you. This is a wonderful award, as we said, in honour of our friend Robin. And it's my pleasure to... The cheque comes in the post later. It's my pleasure to give you your medal and your scroll. Congratulations
thank you very
and thank you. There. These are always the lovely keepsakes. Okay, thank you very much for coming, everybody.